And it's my great pleasure today to introduce Ginger Shultz from the University of Michigan. We're all friends here. Ginger got her PhD in polymer chemistry at the University of Oregon and actually transitioned to chemistry education research by doing a postdoc with Brian Coppola, who many of us know. She then transitioned to another postdoctoral fellowship and then was hired as assistant professor in chemistry education research in the chemistry department at Michigan. And I think she's at the vanguard or on the leading edge of a number of assistant professor chemistry education researchers who have in research chemistry departments who are starting out their CER careers there. And this is an enormously promising development. We're thrilled. And certainly Ginger is one of the stars. She's in her 4th year as assistant professor, and she's going to talk to us about capturing student reasoning, about molecular structure and behavior.
Thank you. Thanks, Melanie. That was a really nice introduction. Thank you. Also, thank you for inviting me. I was saying earlier, it's really nice to come and give a talk to education-centered group, right? So often I'm giving talks in chemistry departments, and there are a lot of different things that I'm considering when speaking to that audience. And so this is really nice. It's also nice to, see friends and neighbors down the road, and to do that. And I've, known about the Create for STEM Institute for a long time and been really curious to see what's going on over here. So this is exciting for me on many levels. So what I'm going to talk about today is, as Melanie said, I'm really going to be talking about reasoning and different ways that we've looked at reasoning in my group. So we have many project areas. So we're interested in how college level teaching in chemistry occurs and how people learn to do that. We're interested in writing to learn. That's probably the most widely known project. And then we've started in this area, which I kind of think about as chemistry thinking. And there are a lot of things that are kind of falling under that, and that's taking shape. But this common thread across all of these, and I really didn't realize this, and I didn't do it intentionally, I didn't realize it until the last year, was reasoning. And I thought this is a good way, this is a good thread to pull and to present kind of little things from different areas to show how we're thinking about reasoning in general. So I thought it would be nice to kind of define reasoning for ourselves and think about that, because I think it's something that can feel very nebulous. And so this isn't a rhetorical question. What I would really like is to ask a student in the audience to say what they think we mean by reasoning. And we'll give lots of time to think about it. So part of it is how someone understands something. Yeah. Does anybody want to build on that?
I think also their process, the modes that they're going through to come to an understanding of how they're making meaning. That's part of it.
Okay. Great. So kind of priming our thinking to think about reasoning. So I also thought, let's go to the dictionary. And so this is a special dictionary, the Dictionary of Psychology. So we can start there and start with a fine definition. Reasoning, it is a noun. I think it's interesting that it's a noun because it's so active. In some ways, it feels like it should be a verb. And it's thinking in which logical processes of an induction or deductive character are used to draw conclusions from facts or premises. So I like this definition. I like using this as a place to start because I think often we can use reasoning as synonymous with thinking, but it isn't synonymous, it's something more. Right? There's more to it. As you said, it's a process. There's a logical process, and we're drawing from different things, facts and premises. Okay, so then let's transition a little bit and think about how do we think about reasoning in terms of chemistry. I know not everyone in here is a chemist, but if we were asking a student to solve this problem in which we wanted them to rank these reactions from least favored to most favored, there's a process of reasoning that they would go through, drawing on what they know, perhaps about trends in the periodic table, what do they know about acids and bases and how they react together, and those sorts of things. So there are things that they're drawing from, and there's a logic that they're going to follow as they solve this problem. So we can think about it in a chemistry way. And then finally, we can think about it in an education research way. And so I've pulled this together. So there are a number of different ways in chemistry education research community that we have looked at reasoning, so related to representations. And I think that many of these can be important across sciences, not just in chemistry, but I think that has particular meaning for chemists. There's mathematical reasoning, and so Marcy Towns, for example, has thought about that in relation to chemistry quite a bit. Conceptual reasoning, there's been a lot of attention to mechanistic reasoning in chemistry, thinking about organic chemistry teaching, but of course mechanistic reasoning, there are mechanisms all across science, not just in chemical reactions, chemical reasoning, and then argumentation. So those are all of the different ways that we can really focus in on reasoning, and that help us to see that we can look at reasoning as a very precise thing, but we can also really pull different threads out of thinking about reasoning, and that's how we've done it in CER. So what I'm going to talk about first from my group, so the first two things I'm going to talk about are ways that we've tried to capture students' reasoning in their writing. So as I said, there's a big part of my group we're really interested in writing to learn, and so essentially we have thousands and thousands of writing assignments from students. I think Melanie can probably identify with having lots of examples of student work and writing that you can draw from. And so we really want to know, if we're thinking about reasoning, that is more than just a conceptual understanding, and it becomes very complex. And so we want to understand how we can look at students' reasoning and examine that out of their writing. And in this case, it's a longer piece of writing. This is a writing assignment, and I haven't put all the details here, but this is a writing assignment that we did in general chemistry. And it's essentially asking students to write an argument about that's related to climate change, based on this data that was presented to them. And the rhetorical context was, you're on Facebook, as many of us so often are, and you see somebody reposting something, and they're interpreting it at face value and not really thinking about what it means. So how would you respond to this person who is interpreting this data in that way and using it as an argument against that global warming is occurring? So the important piece about this is it does push them and has the potential to engage them in argumentative reasoning. But the other piece of this is that it also draws in a really important concept or idea from general chemistry, which is chemical equilibria. So they're having to draw on their chemistry knowledge in order to explain this data and in order to engage in the argument. And so, part of what we do is thinking about how do we write prompts or assignment descriptions for writing assignments that have the potential to engage students in this, and what are all the things that we want to be present in that. So I'm not going to get too much into the experimental details, but we had a really large corpus of general chemistry's students' arguments based on this writing assignment. So we took just 300 of the assignments, and we adapted a framework that Grinberg and Hand had posted. And this was for the science writing heuristic originally, if you're familiar with that. And so we wanted to see, could this be used for this writing and for different styles of writing aside from the science writing heuristic? And so what we did was apply this and to see if it could be applied to these writing assignments that we had. So I want to walk you through this framework and how we were thinking about it. So essentially, there are a number of what we would, or what they called cognitive operations. The way that you can think about what a cognitive operation is it's a particular move in the writing, right, that represents something that they're trying to do related to their argument. So something that has lower cognitive complexity, for example, a definition, that requires what we would say drawing on one ontological domain. And I'm going to say more about that in a second. What we can increase in complexity to things that have only two domains, so a cause and effect kind of move or operation, all the way to something that has multiple domains, so deduction and argumentation. So those become the most complex things that students do. So essentially, we applied this to this large amount of writing, and we did the usual, looking for agreement between people who were coding this, and that was a really long process because these are writing assignments that are about a page and a half, so it's quite a bit of writing, and so that was a substantial amount of work that was done by Alina Moon when she was in the group. Okay, so coming back to this idea of what do we mean by a domain? So if we have a single domain, and we're talking about a comparison, so this you could think about this as being the domain, this single, not a sphere, sphere-like object that relating two ideas, so CO2 rise and pH fall, relating those two, seeing that those are inversely related, so that makes the comparison a single domain. So there are two ideas that go into that. So here's an example of something that has two domains. So for a claim, so you have an observation goes into a claim. So notice that an observation is one of our lower cognitive operations, and that has multiple ideas in it, so pH, CO2, and equilibria. And then it also includes an explanation, and that explanation appeals to what the student knows about Le Chatelier's principle. And so those are the two ontological domains that go into this one cognitive operation. So that's the way that we were thinking about it. And you can also look, so this would be an example of two sentences that together represented a claim. So while it isn't known to all that pH and the concentration of CO2 in the atmosphere is related, it actually is, using the following set of equilibrium principles and Le Chatelier's principle, or systems in Le Chatelier's principle, this can easily be explained. So they're making an observation based on what they're seeing in the data, and then they're appealing to Le Chatelier's principle, or beginning to incorporate that in their reasoning here. The other thing that I want to add while you see this quote is that what you might imagine is some of these operations could appear in a single sentence, and some of them are multiple sentences. So our unit could vary quite a lot, right? So often we see a definition in a single sentence. An argument could be an entire passage. So that complicated things when we were applying this. Okay, so once we had coded all of this with our cognitive operations, we wanted to get a sense of the relative frequency. How often were students using each of these? And so the first thing that makes this a little difficult is that you'll see these numbers in parentheses by each operation. Those are the numbers that are associated with the cognitive complexity of that operation. So an observation is low cognitive complexity, an argument is the highest cognitive complexity. So there wasn't a discernible trend necessarily in terms of the relation of the complexity of the operation and the frequency of its appearance. And this is also an absolute number. So that's the number of times across the 300 writing samples that we saw and encoded for an observation. So there wasn't a lot that was useful to us in this, and so we wanted to do a little bit more. So Alina came up with something called a single metric, which she called the cognitive complexity metric. And that used a combination of their cognitive operation score. So that's that score 1 through 10 in terms of its complexity, the number of sentences that were used in that over the total number of sentences in the essay. And that would give us our cognitive complexity. So we were able to use that then to pull apart or see patterns in terms of what was happening. So one thing that we wanted to do was how does this, is there a relationship between this metric and other variables and external variables in particular? And so the total number of operations was inversely related to cognitive complexity, which shows that students who were writing in a more complex way were using fewer moves, essentially, in their writing, and they were using fewer operations overall. And then the other thing we noticed, there was no association or no significant association or relationship between the metric and any of these other things that we had readily available about our students. So their grade in the course, we have chemistry and math placement, ACT math, their GPA, their gender, their ethnicity, nothing. So we wouldn't necessarily expect those to be associated, right? Because this is maybe a writing specific thing. But I think one thing that we've entertained is this idea that, if this is something that we want our students to know and be able to do, we're not assessing it, right? In any of the standard ways that we look at students. We couldn't get our hands on anything that was writing related, and we're working on that now because we want to see if there's a relationship there. So the next thing that we did is we wanted to know if there was a relationship between accuracy and cognitive complexity. And part of the reason we wanted to know that is that we shared a small subset of the essays with general chemistry instructors and asked them to rank them in terms of the quality of the essay, essentially. And what we found was that if there was scientifically incorrect information in the essay, that would be lower ranked regardless of how sophisticated the argument was. And so there was a tendency by faculty to look mostly at the accuracy of the content as opposed to really thinking about the argument. And so we wanted to know if that was carried out in this cognitive complexity. And so we saw that we essentially just counted the number of incorrect sentences in each of these and then looked at, or instances of something being incorrect, and then the number of operations for each of these. And there wasn't a significant difference. You can see that for some of these, there are a little bit more, but the other thing to remember is that the higher complexity operations are multi-sentence things and longer, much longer than some of the simpler ones. And so they would be more likely to have an accurate item present. Okay, so the next thing that we did, let's see, did I turn it off? Oh, you know what, I have to update my software, sorry about that. Okay, okay, so the next thing that Alina did was she used this cognitive complexity metric to sort the essays into low, medium, and high complexity tiers so that we could compare and say, are there patterns in the way that they are drafting their arguments? And so we had something to compare from that. So what I'm first showing you is something that an example of something that appeared in the lower complexity tier. So what you'll see, and this is more or less in the order of what had happened, and so you'll see the operation and then a paraphrase, because these are long essays, of what that was related to in the student's essay. And this is a very typical pattern. So you'll see someone making a claim, providing a definition, and then there's a number of things that are observations. And these in particular are lower complexity operations, and then only a couple of higher complexity operations. So a long series of lower complexity, and then only a few of higher complexity operations. If you compare that to a high complexity piece of writing, you'll see first that there are fewer operations overall, and that's consistent with the other analysis that we had done. But the majority of these are higher complexity. So in this case, they had a deduction, cause and effect, and an argumentative or argumentation operation, and only one definition, right? So very different in terms of the patterns and the feel of the writing, and that was we felt that was really revealing something about what students were able to do. Okay, so and then to just kind of bring this all together, you can see that same pattern represented in a different way. So if we compare again the low tier to the high tier, in terms of the number of uses that you would typically see, you'll see that students, again, they're using these lower complexity operations for the lower tier quite a lot, and then for the higher tier, there's fewer moves, and more of those moves are going to be the higher complexity operations. So for us, this has several implications. The first thing is that we felt that the framework was very useful, but we had to have something more to help us kind of interpret and think about what was going on. And so it turns out that this complexity score, we felt that was very useful for us. And so those things in combination, I think, is a really useful way to think about how you might holistically assess student writing. The other thing is that there's more that we would like to do, more that we think that we can do. For example, thinking about how likely is one operation to appear after another. We've started looking at that, and so for the lower complexity writing, and this appeared in the example that I saw, you'd see there's a much higher likelihood that students are going to go from an observation to an observation as opposed to something else. And then that is very different for the higher complexity writing. And then this idea that we're measuring something that is potentially unique that we don't normally measure about students, right? So we have all of these things, GPA and placement tests and that sort of thing, that are not being measured. And so kind of pushing on this idea that what should we be assessing for, especially as we move towards engaging students in science practices and other things besides just facts about science. Okay, so that's it for that project. I'm going to transition. This is another example where we've looked at writing, for those of you who are in chemistry education research, you'll know there's been a lot of excitement recently in the last few years. It's almost like exploded, this attention to mechanistic reasoning and thinking about how students learn organic chemistry mechanisms. So I'm interested in this partly because I teach organic chemistry, and of course I practice what I preach, and I use writing in my organic chemistry class. And at some point I realized that I wanted to push past just using writing to promote conceptual understanding, that I wanted writing to help students engage with what they were learning in different ways in reasoning and help potentially change the way that mechanisms were being taught and doing that. So it's kind of interest for me for different reasons, not just for a research purpose, but also because as someone who teaches organic chemistry, I really want to do this better. So this was a project by Field Watts. So he's a second-year graduate student in my group and has been really productive, as you'll see. So in talking about shifting towards mechanistic reasoning, I just want to touch back on what I said earlier, that chemists do not have, we don't own mechanisms. Mechanisms are across science, and we can think about that in different ways. So photosynthesis is a mechanism. You can think about mechanisms in psychology. And essentially what we do as scientists is we propose mechanisms to explain natural phenomena. Right, so that's all this is photosynthesis is a natural phenomenon, and we can propose a mechanism and study that as a way to study that as researchers. So that's what scientists do. If we look at, Russ, we've read a lot of their work, and they've thought about mechanistic reasoning across sciences, and they have three sort of components of reasoning that they put out there: that it should be causal, it's built from experience, and it describes underlying structure. So that's kind of the basis that we are thinking about as we were thinking about as we did this study. So to bring this more into chemistry from broader across sciences and thinking about this in chemistry, we know that we talk about reaction mechanisms in chemistry. That's a way of helping to explain and predict outcomes of reactions. So it means something very particular to chemists. It also requires what's something called process-oriented problem solving, right? And we don't often engage students in this in a way, right? Or in a particular way. And some of the ways that we teach it, I think have an effect, and other people have suggested this, have an effect on the way that they're reasoning and problem solving. So students have a tendency, for example, to use a product orientation to their problem solving, where essentially they're looking to the product of the reaction to help them reason through all of the steps in the reaction. And so several people have shown that. There are also other things that students should be considering. We don't necessarily teach them to consider this, or we don't make it important for them so that they're thinking about it. For example, alternative reaction pathways. We show them the most productive pathway, so that's what they focus on. We don't talk much about the dynamic nature. We represent these mechanisms as symbols, and so they appear very static to students, and so they often don't think about it that way. And we also don't teach them necessarily to think about these as chemically reasonable steps. So does this even make sense based on your foundational understanding of reactivity and structures and properties? Okay, so this is the writing prompt, or the writing assignment, with all of the details pulled out. But essentially, what we wanted students to do was to write about a mechanism, but at the same time, we also have this goal that we want to help chemistry feel relevant to the students. And so many of our students are pre-med and pre-health, and so we decided to use as the object of this assignment description thalidomide, which was used to be used as for pregnant women to help with their nausea and other things, and then they found out that it was a teratogen, which is really bad. And so it was off the market for a while, and then recently it's been found that this actually has other properties that are useful in other medical cases. And so we present this idea to the students as their exigency for thinking about why they want to talk about the mechanism that's going on here. And so there's an entire rhetorical context that we're thinking about when they're engaging in this. So they write not a 500 and 754 exactly. It's probably 750. I don't know why that 4 is there. But essentially, so we provide the background, as I just mentioned, and what we want them to do is think about the hydrolysis mechanism. There's also racemization that's happening here that they talk about. And we want them to describe the mechanism. And then they also propose an analog. Because our thinking is, if they understand how this happens, it requires an understanding of that in order to propose an analog that actually makes sense, right? So we're giving them something that requires meaning making and problem solving in this prompt. Okay, so I'm going to skip that. Okay, so in this, taking somewhat of a similar approach, we looked to the broader science education literature and thinking about how, and starting with an analytical framework from that. So this was also from Rosemary Russ and these authors here. And it has been applied by other people in chemistry education in thinking about mechanistic reasoning. So there are 7 different categories that they have identified in mechanistic reasoning. This was initially used to analyze student discourse. So we're taking this and trying to adapt it for writing. And there are all of these steps. So there's describing the target phenomenon, identifying setup conditions, and so that would be the phenomenon is thalidomide, and it undergoes this hydrolysis. Entities would be the molecules or the pieces of molecules that are in there. Activities would be the how the molecules are interacting with each other, or the parts of molecules are interacting with each other, and so forth. So those 7 pieces were identified. This could be applied and was applied to other mechanisms that are not chemistry specific, but we wanted to use it in this case. So Winfield looked at this writing, and I don't have the N up here. I'm pretty sure this was close to 300 as well, about that number of assignments. He ended up using single sentences, so he didn't have the problem that Alina had in that the units were different. So he looked at single sentence units, and when he applied this analytical framework, he really found that there were 3 that were present in the most salient ways. And also there were some that were kind of hidden in others that he didn't look at. So we focused on these 3. So describing the target phenomenon, which could include the overview of hydrolysis and then identifying the 2 reaction pathways that could occur. Then talking about the setup conditions, which could relate to what needs to happen in order for the reaction to proceed. And then identifying activities. So this is the part that we're really interested in. So how are the students describing electron movement and changes in bonding? And those were things that we saw quite a lot. So you can see 99% to 100% of students use this at least once in their writing. The other thing that we saw alongside that was chemistry reasoning. So in what ways were students appealing to what they knew about chemistry in order to, in their reasoning here. So because this was a hydrolysis, essentially, many students used an acid-base explanation. I'm really sorry for those of you who are chemists in this case. So nucleophile, electrophile charge, resonance, and electron activity. So you would need a really deep chemistry background to see and actually really thinking about this reaction to understand why a student wouldn't necessarily use a resonance explanation very much, or you wouldn't expect that, and maybe even electronegativity explanation. So what we're going to focus on, though, are the relationship between this component of the mechanistic reasoning, which is the identifying activities, and then also the chemistry reasoning, because we wanted to really understand how those were operating together. With students, and we were seeing some things that we thought were kind of interesting. So in terms of identifying activities, these break down in these particular ways. And I think for this audience, I'm not going to dig into that too much. But one really important thing to think about is we can divide these as explicit and implicit. So explicit is that there's something in the symbol, right, of the molecule, the representation of the molecule that is very clearly represented to the student and they can invoke. there are things that aren't clear to the student that they would have to think more deeply in order to pull that out. And those are very different. And what we know from the literature is that students have a harder time with the things that are implicit from the representations. And so we wanted to capture those two things. Okay, and so electron movement, that was one of the ones we talked about before, and then also thinking about this in terms of changes in bonding. Okay, and then this is an example of a quote, of a sentence, sorry, that was coded for one of these. So the oxygen in the water molecule then attacks the carbon in the carbonyl through electron pushing, forms a tetrahedral intermediate. Okay, so there's lots of things that we can pull apart from that, but you know, essentially that was kind of what we were looking at. So in terms of chemistry reasoning, it broke down into the 5 categories that I mentioned before. But one thing that we really noticed, so if we look at the quote here, actually let me go back a little bit because I forgot to talk about this. Notice that they're using this word attacks, right? And I think we use that quite a lot, this kind of a colloquial way of trying to help students visualize or think about what's happening. So attacks appears again here, right? So that was one of the ways, a kind of a word that if that appeared, we're saying, okay, there's something that's connecting their discussion of electron movement and that element of mechanistic reasoning to the chemical reasoning that they're having. So that was one of the things that got us interested, and we wanted to kind of pursue more. So what we did was first look at this visually. So this is a set of Venn diagrams that allowed us to look at essentially the co-appearance of codes. And the overlap here is representative of how many sentences out of the total did these appear together. So if we look and if we narrow in on this and think about this as a particular case, we can think about, so there's an explicit description of electron movement, and how often does that appear with these other elements of chemistry reasoning, right? So we can see if we think about an acid-base explanation, that overlap is much smaller, but if we compare that to a charge explanation or a nucleophile-electrophile explanation, then there's a bit more of an overlap. So that's great. Qualitatively, you can kind of see that. Well, we wanted to capture it in a more quantitative way. So Field, the student who worked on this, he actually found a metric in data science that we're using for, that's been used in machine learning and that sort of thing called lift. And essentially, that gives us a sense of how often two things are appearing together. So essentially, we take the probability of code A and code B, whatever those are, appearing together. So that could be the explicit electron movement and the acid-base explanation, and then the probability of one appearing by itself and the other one appearing, and that gives us lift. So if the lift is less than 1, that means that the codes will appear together less often than would be expected by chance. If it's greater than 1, then they appear together more often than expected by chance. So it's just giving us a single number that we can think about to help compare what is going on. So now we can go back and look at that lift number, and that gives us something more precise than our Venn diagrams. So essentially, thinking about the explicit electron movement and using that in the mechanistic reasoning, and how often are we seeing that with acid-base explanations, nucleophile, electrophile, and charge explanations. So you'll see students are not using that associated, they're much less likely than by chance to use that alongside an acid-base acid-base explanation, but much more likely in a nucleophile electrophile. So the chemists in the room, especially those that are familiar with the chemistry education literature, one of the things, at least this is what I thought about immediately when I saw this, is that we know the way that organic chemistry is taught, we put a lot more emphasis on the Bronsted-Lowry definition of acids and bases and less on Lewis, right? So if we were pushing forward a Lewis acid-base model, then we might see something different here. So I think that this is telling us something about the way that we're teaching organic chemistry and what students are more likely to draw from when they're creating these explanations. So this is also an example of that in the writing, because I want to go back and think about it as a case. So how are these really appearing together outside of the numbers? So the student is talking about the carbonyl group between the two nitrogens and acidity of the molecule. So here is where they're explicitly talking about electron movement. So electron density, and I always find it really interesting how they use a mixture of their own terms and try to pull in terms from class. So electron density, being able to move toward the oxygen, makes it more reactive, so it can be protonated. So here we see their discussion of the electron movement associated with a Bronsted-Lowry definition of acids, which creates a positive oxygen. So that would be the charge explanation, and so forth. So these are the different ways that we're seeing it, but you can see in this a whole lot of the way that we think about acids in terms of an acid being a proton donor and a base being a proton acceptor. And so deprotonate, deprotonate, protonate. And that's the language we use when we're teaching. So of course students are going to use that, right, rather than talking about electrons being accepted and donating. Okay, so, and I already said that, so we saw that their discussion of electron movement tends to be implicit rather than explicit when using the Bronsted-Lowry. Okay, so the implications of this. So very similar in some respects to Alina's study in terms of adapting a framework, and that we found it very useful to have some kind of metrics that helps us to capture what we're interested in. In this case, we used something called a lift metric that helped us to think about the co-occurrence of reasoning and mechanistic reasoning and chemical reasoning. And we're really interested now in thinking about how the framework and the metric can be applied in further ways to examine patterns in student writing. For example, building on this, so how likely are they to explicitly describe electron movement while also appealing to the Bronsted-Lowry model? Okay, so lingering questions from these first two studies. So these were both really focused on student writing, and we're really interested in the potential of writing to help students engage in this. But one of the things that we know, and these longer pieces of writing are not necessarily easy to pull things out of, and especially when we get into more complex things involved in reasoning. So that's something that we're working on. So how do they function with other types of reasoning and other types of explanations? But the other thing we've really been thinking a lot about is what are the features of assignment prompts that elicit these more complex, for students to do this? What is the potential? What are the things that have the greatest potential to help students do this? And I would say, even with Field's writing assignment, that was an assignment description that we used 2 years ago, and we've learned a ton since then about how students are going to engage with this through interviews and that sort of thing. But we are hoping that these frameworks and metrics will help us to really look at the features of the assignments and help us to do a better job of creating assignments that are going to be that have a greater potential for engaging students in this. So that's kind of where we're at with that. So now I'm going to transition to a really different kind of reasoning, and this also really gets into the chemistry. So thinking about how students reason during NMR spectral interpretation. So this is just a form of data that is very much used in organic chemistry and then later across the curriculum. So a graduate student, Megan Connor, she's a 4th year in my group, did this work. So for those of you who aren't chemists, this is an essential technique. It's probably one of the number one spectroscopic techniques or ways that students can collect data. And so there's a lot of opportunity there for thinking about how students interpret this data and how they reason about it. So we think of it as a really rich place to think about how students do that. It's notoriously difficult to teach and learn, in part because of its complexity. It invokes a lot of different topics and understanding in order to solve these problems. And so it's really challenging, and so we find it interesting for that reason. And we know a little bit, but we could certainly know more about how students learn to interpret this and how students learn to teach this topic. So we're interested in that. I'm going to skip that. So in terms of what's been done so far, what we do see is a really large number of publications that are really on practice ideas. So if someone will teach this, they teach it a lot, and they have some really great idea about how they want to teach it. And there are a lot of those kinds of reports. I think what those show us is that that people who are teaching chemistry care about this a lot, right? That this is an important topic for them. So I think that invites more research in terms of understanding how to better teach it and to support those ideas. And there are relatively fewer studies examining how it's taught and learned. So this is an example. So some people have, and as have we, begun to use eye tracking in combination with other methods to try to understand that. To me, the first the paper that got me excited about thinking about this and that appealed to me as both an instructor as well as a researcher was this paper by George Bowdener, which he called non-mathematical problem solving. And I think a lot of the studies have followed after that in thinking about this as in terms of problem solving in that way. And what they did was study students who were interpreting this and using it, NMR spectra and using it in problem solving, and they found that the more successful participants were more likely to do these 4 things. So use consistent approaches, draw fragments as they worked, more carefully mine spectral data, and check their final answer. So when I read this paper, I immediately went to class when I was teaching organic chemistry and said, okay, I know how, I'm going to teach you how to do this, right? It excited me as an instructor, but then of course I learned that you can't just give a list of things. It can become a heuristic, but it has also made me think about it a lot, and I think this was, to me, the thing that excited me about the work. And then more recently, and this is probably the most recent study to come out, is this work from Melanie's group with Ryan Stowe. I know many of you know him. And in terms of spectral interpretation and how that relates to arguing from evidence. And I think this was the first one that really changed from kind of a problem-solving approach to thinking about how students learn to do spectral interpretation, to relating this to something, other things, right? So having to do with reasoning, argumentation, and that sort of thing. So the main findings from this paper, which you could lift out of the abstract, students could analyze and interpret data. So in terms of these individual things, they were able to interpret the data and analyze them. But their success in completing these were not necessarily related to their ability to assemble these and use them in an argument from evidence, right? So those were in some way disconnected. And then the final thing that they found was that the prompts, so this was coming from assessments, the structures of the prompts, so the way that those were organized, didn't necessarily have an impact on students' success in coordinating those claims. And the reason that I bring those up, particularly this last one, is, if you recall from where we were landing with our writing, is we know that we're paying a lot of attention to the features of assignments and thinking about how they can promote and get students to engage in what we want them to engage in. But that's not the whole story, and it's really hard to do, right? So we were really interested in that finding. Okay, so moving on to how we're thinking about it. So we started in this thinking about it from the beginning with dual process theory. So if you're not familiar with this, it basically categorizes our reasoning as type 1 and type 2. So type 1, meaning that it's very quick and kind of on your intuition or your beliefs, and you kind of look at things superficially and do things very quickly. As compared to type 2, it's slower and effortful, and you're pulling things more deeply out of your brain and thinking about it in that way. So we have type 1 and type 2. If we apply this to that same example that I invoked in the beginning when we're thinking about reasoning, so can we rank these reactions from least favored to most favored, then how would a student who was using type 1 versus type 2 apply this? So if they're using type 1, then they're going to go with something very quick and automatic. And a student might go, oh, I recognize hydrochloric acid. And because they're familiar with that, then they're very quickly going to put them in this order. And basically based on familiarity, rather than thinking more deeply, as you might in a type 2 reasoning, where you're thinking about periodic trends and how that relates to acid strength and that sort of thing, and also the stability of the base and acid. Okay, so that's just an example of that, just to help us think about what this means in terms of chemistry. So this is how we're thinking about it. So we, I guess, were inspired by Meyer and Talancura in 2013, where they described it in this way, and then we're applying this to NMR. They use it in a different way. So thinking about how do we have, so students begin with a basic understanding of NMR principles, or they're taught these things. How do they use those, and how do they go to what we might consider to be sophisticated reasoning, right? So in terms of NMR, that would mean, as Bowdener said, carefully mining all of the things from the spectra, so identifying, assessing all of the relevant spectral cues, and then making valid chemical assumptions as part of that reasoning. So we thought that that was really useful for the way that we wanted to look at that. And so we can kind of divide this in two ways. We divided it as conceptual understanding and modes of reasoning. And so we're thinking about this in terms of looking at students' reasoning in terms of the valid chemical assumptions that they made as well as the invalid ones. And we can think about invalid chemical assumptions as potentially being related to problematic type 2 reasoning, meaning they're thinking deeply and pulling information out, but it's the information wrong or right that may not be helpful in their reasoning. And then in terms of modes of reasoning, what are productive reasoning strategies versus unproductive reasoning strategies? So in terms of type 1, it may be that they're using a heuristic, for example, that could serve them in many situations, but isn't appropriate in the situation that they're using. So that's how we're thinking about it overall. I'm going to focus on the invalid chemical assumptions and unproductive reasoning. We're looking at this together as a full thing, but those were the ones for a couple of reasons that we looked at first. Okay, so in terms of how we captured their reasoning, we did something that was a bit more complicated than looking at their writing. So I want to walk over that. Okay, so we developed a set of tasks. We wanted them to incorporate difficult features and be authentic for the students. So what we did was interview a number of faculty who are experienced with teaching NMR to get at what were the things that would be difficult for their students so that we could try to match this to what would be appropriate for students who would be taking sophomore level organic chemistry. And then we developed the 3 tasks and what we would call day-to-day problems of chemists. So Jeff Raker and Marcy Towns put out a paper where they had interviewed and practicing chemists to identify what they would normally routinely be. And then we piloted them to make sure that we were hitting the right difficulty level. And then our data collection, we used a combination of eye tracking and retrospective think aloud. I'm not going to get into the eye tracking too much. It allows you to think about what students are attending to and what they're moving back and forth between, and that's connected to what they're thinking about. We used that, or for these purposes, we really used the eye tracking as a way to support our retrospective think aloud interview. So in this case, we wanted the students to solve the problem. We tracked what they were looking at, and then we replayed for them what they were looking at in order to help them to elicit what they were thinking while they were solving the problem. And in this way, we could pause and say, why do you think that you were looking at that amine group in the appropriate anamide? So that was kind of the basis of our study. We then analyzed them. I guess we were thinking about this in cognitive constraints at the time. So essentially, we were looking at those assumptions that we're talking about, so the invalid assumptions, and then the heuristics that they were using, and we did this process. And these were some of what we saw. So in terms of invalid chemical assumptions, I'm not going to talk about the valid chemical assumptions today, but there were some things that we noticed. So for example, would be this assumption that the N+1 rule is used. So if you're not a chemist, the N+1 rule is a heuristic that we teach students that helps them to interpret a feature on the spectrum. So it works most of the time, but there are exceptions when it doesn't work. And if the student doesn't remember what those exceptions are, that can be problematic for them. And a lot of students hold on to that very tightly, as they tend to do with heuristics. Let's see. Another one would be that spectral data should be absolute. So in this case, there's this really broad peak on this infrared spectrum, and right next to that is a really tiny peak. So the students are missing that peak, and they're assuming that because it's so small, it doesn't matter, right? So that's an example of that. I'm going to skip a couple of these just for the sense of time. Let's see. So then we also looked at their reasoning strategies. So some of the strategies, just to give you a sense of what we were seeing, so there's something called one reason decision making. So they interpreted one piece of the peak, or one piece of the spectrum in a particular way. So they said those peaks couldn't be singlets, and because they thought the peaks couldn't be singlets, they based their entire judgment about the reaction on that, or about their interpretation of the spectrum based on that one thing. And reduction, affective judgment, so sometimes they're just going with a feeling, which makes us think of type 1 reasoning, as you recall. And then we So once we had all of these assumptions and heuristics, then we wanted to know how problematic are these for students? Because these are all part of the thinking process, and they're not necessarily bad, right? But in what combinations are they problematic for students and prevent them from being successful? And so the coefficient above the arrow, that represents the likelihood that if they use that heuristic, for example, that they would end up providing the wrong answer. And so we found, you see, one reason decision making, something called rigidity and generalization, that if students, if students were using that in their reasoning, then they were much likely, or very likely, in fact, in this case, absolutely likely to be not be successful and to determine the wrong answer in that. And some of these were more than others, and some weren't a problem at all for the students that we interviewed. So that kind of gave a sense of what are the patterns of reasoning that students are using and the assumptions that they're making that could be problematic, and things that don't appear to be problematic, and we can think about that. We can also use that in terms of a Venn diagram and think about that, because we like Venn diagrams apparently in my group. So we have, these problematic heuristics, so if they have one reason decision making, which we talked about, rigidity, which we didn't, in generalization, and those things tied together with this invalid assumption, which is that the n+1 rule should always hold. If those things were all used in combination, then the students were going to give an incorrect response, and those were the 6 students. So this was a qualitative study, and so we don't know how generalizable that is, and to the degree that this is specific to the tasks that they were doing. But I think it says that or at least gives a start to how we might think about the different things that, that play into students when they're reasoning into this. Okay, so what we found was that the problematic components of students' reasoning were usually due to a combination of the underlying assumptions and heuristics. We found, like Bowdener did, that students who were successful in solving the tasks evaluated their spectral cues differently than those who didn't, and that particular invalid assumptions in reasoning strategies would constrain the students' reasoning the most. So what we're continuing to do now, we've actually now coded all of the valid and invalid, or valid assumptions alongside the invalid ones, and looked at their reasoning strategies. But what we've realized is that we really want to get a greater difference between the students, and so, in our participants. So we've actually started to interview and collect data with graduate students and postdocs and faculty even, which was exciting for us. So we're pushing on this, but I think we want to go there, and we want to get more expert reasoning in there so that we can look at it in a different way. So that's where we are with that, and that was it. Okay, so basically different ways that we've looked at reasoning. So we've looked at argumentative reasoning, mechanistic reasoning, and then students' reasoning while they were solving data and using the evidence from that data in solving a problem. So I want to acknowledge, so this is my group. This doesn't include everyone. We do rotations, so there are people in this group who they're going to be in the group, but we have to do rotations first, so we can't say it officially. So Megan Connor, as I said, she did the NMR work. Field Watts did the mechanistic reasoning, and then Alina Moon, I know a lot of you know her. She's at Nebraska, and she did the argumentative reasoning and these sources for funding, and I'm happy to answer any questions.
Floor is open for questions. Rob.
So a couple of questions. One, I really like this question about the thalidomide opposing analogs. But do you give them some constraints? Because obviously you can have an all-carbon structure with no chance of hydrolysis.
Yeah.
But that's not an analog. So do you give them constraints?
We do give them constraints, and we've tried to do it in a way that's consistent with how they're being taught organic chemistry. So most of our faculty try to help students to understand that small changes can make a big difference. So in the prompt it's basically to say, this should be a small change, right? That you're not changing the entire structure. Also because, to be consistent, but also, I mean, for the reason that you said, but also because they're they're not learning as much. And we also have a definition in there in terms of what is an analog, right? And what should that be, because they may not know that as well. But yeah, that definitely came up, and we've had to tweak the assignment description to narrow them in. And we also have undergraduate writing tutors who help the students, and we train them because students will come to them and say, is this a good analog? And helping them problem solve and help the students to think through, what do you really need to do? And to push them back towards thinking about the mechanism of the reaction and using that information to propose their analog.
And then in the NMR, so in terms of the eye tracking, is there a general trend as to what students look at first?
So we've been looking at it in terms of successful and unsuccessful problem solvers. And the unsuccessful ones, it's not in terms of what they look at first, it's more that they're very erratic and they're looking all over the place. And I know other people have seen that. And then also what they're transitioning to. So the more successful people, they go between, let me go back because I think it's worth showing on the spectrum if I can get there. Yeah, okay. So the successful problem solvers, they look at a feature of the structure and then they look at the position on the spectrum, right? So they're relating where it appears on this scale to the structure. But the unsuccessful ones are just all over the place. They're looking at different things. They're looking at, yeah. So that's the main thing that we've noticed. But it's hard to say definitively because we just didn't have enough numbers that we were only just approaching something that was statistically significant in terms of looking at the difference. And so that was also one of the reasons that we started to interview more expert problem solvers, I guess, in this. Yeah.
Can you talk about the choice in field work,
Mm-hmm.
breaking things down in terms of sentence units and on the notes frequencies? Why was that necessary? Can you talk a little bit more about that strategy for analysis?
Sentences as opposed to some other unit or something like that?
The whole response in whole and looking at the components of that and looking at co-occurrence more holistically rather than looking at individual sentence as your units and looking for that coherence or whatever.
So, I mean, part of this comes about as someone from the perspective of what are we even seeing that we know should appear from mechanistic reasoning, and then if we look at that, we just have all of these frequencies. And you can pull some things out of that in terms of, that what we saw, that they're more likely to talk about explicit features of the representation as opposed to implicit features, which is, consistent and it's not telling us anything new. And I think some of it just came out of curiosity that didn't seem that interesting to us. And I think at that point, along with doing what was a more deductive coding process, Field was also memoing quite a bit, and in that process, he was just noticing a lot of things that went beyond the mechanistic reasoning framework. I don't know if that comes back to the unit. I think the sentence unit was really just a convenience thing that we weren't seeing multiple sentences being important, and that mattered, and so the sentence just seemed to be the right fit for that. Okay.
So the eye tracking work, you've clearly shown that Cartwright and Bowdener's framework of using flexible strategies isn't really happening for our unsuccessful students. So how does your work kind of help us get students to move away from that rigidity and that snap judgment? Is there anything in the successful that has helped you figure out how to help those students?
Yeah, I mean, in some ways, what I hoped that we were doing is drilling down in a more detailed way, building off of what Bowdener found. I'm hoping that as we get further with the more expert, so because we weren't seeing as remarkable or I guess significant a difference initially, I'm hoping that we'll build on that. I think right now we just aren't seeing the whole picture. Like you can't just look at the invalid assumptions, right? That there's so much more going on when students are solving this, and I can say that some of what Megan is seeing so far in terms of the differences is really interesting, but I am still struggling as an instructor to get students to think flexibly in general, right? Like I don't know how to get students. I can't think of how many times that I think that you have to be flexible, you have to take all the pieces together, and I don't know how to get that to resonate with students. I haven't figured that out yet. I'm hoping this will help us to see that, but right now it's just saying, yeah, that they aren't being flexible, that they're being rigid. But I think we don't know enough about the students who are being flexible to really understand that, and hopefully we'll be there soon.
So can I follow up just
Yeah.
on that? So the work that Ryan did, we were also inspired by Carteret and Bowdener, and we were convinced actually that we could design prompts that would lead students to analyze all the spectra, and we
Yeah.
did this, and I don't know if you read the paper, but there are maybe 10 different prompts with hundreds and hundreds of students interviews, and we never were able, we could get students to analyze the spectra actually. They could do that, and they would tell us the individual bits and pieces of evidence that they could extract from it. And then we get to the, so right down the structure, and typically, unless it was a particularly easy one, about 40% of the students could do it, and we never got higher than that.
Yeah.
And it was dreadfully disturbing. So it's just a follow-up.
Yeah, I did see that in I believe he did a logistic regression of some kind and we haven't gotten that quantitative with it yet. We've really been looking at things in a qualitative way, and that was the thing that stood out to me. Was I was thinking, how can we have such a large quantity? How can we tie that back to the problem? Is that we'll find something and then we'll change the prompt.
Yeah, so that's what
Yeah.
we kept doing. Yeah.
One thing that we have seen, I think, is that the students will move towards the things that are easier for them and not spend as much time on the things that are harder. And that can be in whatever you're talking about. So we will be very explicit in the hard things. No matter how explicit we are, we see a difference in how they're attending to the things that are easier for them versus the things that are difficult. And I think what you're talking, in that example, and then also we've seen this in many cases, is that then taking what they've interpreted and to the argument is more difficult. So it's almost a question, to me it almost feels like, how do you get them to do the more difficult thing and engage in that?
So I like where this question is going about trying to understand student learning and success. And I wonder if one of the difficulties of this is underlying kind of the mechanistic reasoning and other things like epistemological reasoning, right? So clearly there are some ways of knowledge production and practices, and especially like organic chemistry, that are invisible to students.
Yeah.
So I'm wondering if you thought about or have ways of trying to, especially through some of your initial qualitative work, of trying to gauge how students, in terms of student success or student learning, how students are coming to understand what it means to think about how chemists make and do knowledge. Yeah,
so we are looking at that. So Jennifer McCormack-Schmidt, she was a postdoc and moved on to a faculty position. So because I've only talked about the writing in chemistry, we are fortunate that we have people across disciplines doing writing. And so what she has done is looked at the interviews that we've conducted with students in economics and statistics and biology, and is looking at that, thinking about it from an epistemology standpoint. We're not very far along, but there are very clear differences. We also see that with our faculty in the ways that they design the writing assignments. So there's certainly an epistemological perspective that I think we can capture in this writing assignment, but we're just beginning to do that. Right? So yeah, I agree, I guess. Yeah.
Kind of going, since we're on the topic of the writing a little bit here too, and this is maybe less of a chemistry question too, but I read your paper on writing to learn, and I remember just thinking when I got to the end, how do you handle the fact that you have these huge numbers of papers that you're dealing with as an instructor, and how do you feel as an instructor that you can accurately kind of get through these, get them back to the students, and actually kind of do that, not necessarily from a researcher role, but kind of from an instructor role?
Yeah, so that was the nut that we had to crack before we could get people in statistics and economics and all of that to do this, because all of these people are teaching or coordinating classes with thousands of students. So statistics, we have 5,000 students a year taking that, and they are all doing this level of writing. So part of it is you have to think about the assumptions that you have for what it means to give feedback and what it means to assess something. And we believe, and we've shown, that students are very capable of giving each other meaningful and even accurate feedback, just as much as we are. It's just that the more students you have giving feedback, the more likely that they're going to match what the expert feedback would be. So we do track, we use peer review, and we track the students' comments, and we've seen in biology particularly, but in some other instances that the students are very successful in giving feedback. So I think that's a really, I think that attends to the feedback thing. Some of the ways that we have addressed to the assessing part of it for a grade, because at Michigan, if you don't give students a grade, right, they're going to focus on the thing that they do have to get a grade for. I'm sure it's true here. So the question is, what do you need to assess? When you think about a page and a half of writing, do you need to grade it rigorously for everything? No. And in this case, our goal is writing to learn, not learning to write. And so we found that if we are very explicit about the learning goals, and those are carried across into their peer review criteria and in the rubric, we can actually assess them very quickly. So whether we have a team of graduate students, in some places we have teams of undergraduates helping us, you can actually get through quite a few. If you're looking for 2 discrete learning goals, for example, it's actually much quicker than you would think, especially after you've read even a handful of the longer ones. You know where they're going to appear, and it happens very quickly. And so those are kind of the more practical ways that we've got around it. And once faculty get through the first term of seeing that, then they believe what you've been telling them. And so now we have faculty, so that the faculty member in economics who's doing that, he is actually completely changing his exam structures from multiple choice to open response, because he has had so much success with the writing parts.
Hi, so I was also, back to the spectroscopy, I was wondering if you thought about time and that aspect of it as well, and considering that these are really difficult and it does take time to kind of piece through all of this, and how maybe the more successful students are quicker at it and the less successful students aren't, or that kind of aspect.
Yeah. So we haven't looked at the total time to solve it. I think very quickly we realized that we had to make a choice between whether we constrain them on time and whether we leave it open-ended, and we left it open. So that meant that there was a range, and so we probably could look at that, and I imagine that there is a difference in terms of that, but we haven't looked at that yet.
Yeah, because along those lines, like leaving it open-ended, I'm wondering, like, many organic faculty put them on exams, which are in fact not open-ended, and so how does that fit into how we think about how students are doing these kind of assessments?
I mean, we do open-ended exams in organic completely. There are no multiple choice in our organic exams, but
like open
oh
time,
yeah,
like
open
they have
time.
time on an exam, whereas
Yeah,
in this
and they
might
don't.
not.
Yeah. So I mean, we certainly never ask them to write a page and a half of something. And in terms of that, so I think that over time, faculty get really good at figuring out how much time it takes. Usually, sometimes we make a mistake, and then there's a domino effect. But yeah, I don't know. I mean, that would be kind of an interesting thing. Like, I would love to talk to this economics professor in terms of how because he still uses multiple choice. He's just included some open-ended, right? So then that becomes an additional thing, and that makes me curious to ask him, like, how did you just decide how many open-ended ones that you would have, right? I hadn't thought about that at all, because I didn't have to make that change.
So, I'm fascinated with this notion of flexible thinking. And my guess is flexible thinking has to do with depth of knowledge and also fluency in which to use your knowledge. But when you look at that up there, right, this is the amount of knowledge that you have to work between those things is just incredible. And we all know Michigan kids are pretty smart, but they might not have the depth of knowledge, right? They can get to organic chemistry with not necessarily having that depth of knowledge. I wonder if you just talk on that, because I wonder if what you're seeing really has to do with kids really knowing their subject matter, and not only the subject matter of chemistry, but you're doing a lot of the physics here in the last two things too, right? So I don't know if you looked into that at all. To me, that seems like that's what would be related to it somewhat.
Yeah. I mean, so we haven't looked at, we have, I should say that some of the ways, I always think that I want to be careful when I talk about exam scores. So where they, in organic chemistry, the place that they get most of their NMR is in our lab class, the second term lab class. And so we have quizzes, and the quizzes are almost entirely spectroscopy. So that's one way to do it, but we haven't done it as, let's say, a pre-post sort of thing, right? So we could look at it in that way, but we haven't. And this is actually making me think of, so when I was at Purdue a few weeks ago, and I actually was able to talk to George Bowdener about this, and he said, not unlike what you said, that he said, what are you really saying, that the more successful people or the more experienced people, what they used to be type 2 for them is now type 1, right? That the things that experts are much quicker at seeing and being able to pull out the features, and so they can take it a step further. So I agree with that. I can't say that we've looked at it in that way. Is that what you were thinking?
I would just think that having depth of knowledge, I mean, like really knowing what an NH bond is connected up there, right? And how that's going to relate back to the NMR graph is like really critical in making these decisions, right? And you could probably get to second semester chemistry and do pretty good without having really that depth of knowledge that you would need to do that, right? So, anyways, I found it fascinating when you said, you know, the kids who are successful were able to get from looking at the molecule down to the graph, they would know where to go. Or the other kids are kind of wandering all around, they don't know where to go, right?
Yeah.
So that's why I was thinking of like, does it have something to do with like depth of knowledge, and they really understanding what's going on?
Yeah. And I imagine,
So,
Yeah.
so I don't agree with that. I think from our work, we found that they could analyze the spectra and say, well, there's a triplet, it must be adjacent to two hydrogens.
Mm-hmm.
They could do those things. They could say there's an OH group, but what they couldn't do then was put it all together.
Yeah, well, that has to do more with even more flexible thinking, right? Really
Right.
understanding what happens when
Right.
you do that. I don't think
Even-
I don't think we're in disagreement.
Okay. But they could, they did know what the spectrum meant in terms of figuring out what the bits and pieces were.
But it sounded like they knew that by your
Putting-
prompts, right?
Yeah, so the prompts would say, you know, tell us what fragment of the molecule is, you know, from 3 to 4. And they would write down the appropriate fragment. And we would lead them on and on and on until it became obvious that what was, and it never was obvious.
Right, so I wonder what the next prompt would be to get them to synthesize.
I refer you to our paper. Anyway, sorry.
Yeah,
we've got another.
Oh, great.
So I was wondering if you could expand a little bit, because I have the same or a similar comment to Joe, right? In terms of the underlying theory of learning and cognition that's being applied here, right? Because I think this type 1, type 2 thing is awfully simplistic, and you're sort of acknowledging that in some of the comments. I'm wondering if this might not be better kind of construed as in some form of learning progression, right? Or description of expertise development, right? That's a little bit more rich than the kind of binary model.
Yeah, I absolutely agree with that. I mean, and so what you're seeing is kind of a 2 years ago look at the project. And so we're almost to the place right now where I think we can look at this as a progression in terms of what we've done. And we've started to map that to a certain extent. And so I agree, like, you know, so this is just timing in terms of our evolution and our thinking about this project. And our familiarity with what can work. Yeah, so I absolutely agree with that. And we're moving in that direction. Yeah.
Okay, well, if there are no more questions, please join me in thanking Ginger for this. On behalf of Create, these are a few remembrances.
Thank you.
Forget us.
That's very nice.